Hello, my name is Christopher Lee, and I will be presenting one of the NSA tools leaked by Edward Snowden called Quantum Insert. The NSA has been in the news recently after Edward Snowden released classified papers regarding the techniques and tools used by the NSA to spy on both foreign and domestic threats back in May 2013. There has been much controversy over whether or not the NSA should be allowed to spy on American citizens without a warrant. One of the techniques/tools used by the NSA is this thing called Quantum Insert. In this video, I'll be discussing what Quantum Insert is and how to detect Quantum Insert. In the documentation leaked by Edward Snowden, there were many different software suites that were discussed. A couple examples would be Bad Decision or Fox Acid. There is also a software suite called Quantum Theory. Within Quantum Theory, there are other tools like Quantum DNS, Quantum Bot, and then there's Quantum Insert, which is the focus of this video. Quantum Insert has nothing to do with quantum computing. Quantum Insert is a method of attack where a malicious actor can inject a TCP packet into a TCP stream or hijack a TCP stream altogether. This can happen without the victim even knowing. How does Quantum Insert work? Quantum Insert is a TCP injection attack. TCP injection attacks are not a new type of exploit. Kevin Mitnick was able to perform a TCP injection attack to spoof a banking site in the 90s. Up until that attack, it was common practice to use a non-randomized initial sequence number for TCP packets. This allowed Mitnick to easily predict the sequence number to hijack the TCP stream and ultimately spoof the bank's website. After that attack, it became common practice to use randomized sequence and acknowledgement numbers. Modern TCP stream attacks can still predict the sequence and acknowledgement numbers, but it requires more than just being able to see the traffic coming from the victim. Quantum Insert relies on an attacker being able to take control of multiple routers that may be around the victim. The attacker would also need to have a computer with a fast connection loaded with software that can quickly spoof a TCP packet. This computer is called the shooter. For the attacker to know what sequence number is going out, it uses the hijacked router that the victim may possibly use to tip off the shooter on any HTTP requests that the victim has made. This allows the shooter to know when to fire back a response. The main objective of the shooter is to beat the response from the original server that the victim is trying to get a request from. The tip-off is an important part of Quantum Insert. For the attacker to know what the sequence and acknowledgement numbers are, the attacker will need a way to observe or sniff the packets the victim is sending out. The most reliable way would be for an attacker to have an intermediate device between the victim and the actual web server the victim is actually trying to contact. This is where the tip-off comes into play, as the tip-off not only notifies the shooter that the victim is trying to send out an HTTP GET request, but also the sequence number and acknowledgement number of that request. The tip-off can also identify the target using a cookie header to verify the target's computer. In this illustration, we see a typical TCP handshake. The handshake consists of first, the client sending a SYN packet to the web server with a randomized sequence number. Then the web server is sending back a SYN ACK packet with a randomized sequence number and uses a sequence number from the SYN packet +1 as the acknowledgement number. The client then sends back an ACK that generates another randomized sequence number and uses the sequence number from the SYN ACK packet +1 as the acknowledgement number. The sequence number is important because that is how the client and server know what to respond to. The software used to create and maintain the TCP stream uses sequence and acknowledgement numbers as a way of verifying the TCP stream. The software will only listen to replies from TCP packets with the expected sequence number. If the number is not what the software is expecting, then the packet is dropped. The importance of using randomized sequence numbers is so that if a malicious actor is trying to use traffic analysis to listen in on your traffic, it makes it more difficult for the malicious actor to try to spoof a TCP packet. If the sequence numbers are easy to predict, then said malicious actor could hijack your stream using a spoofed TCP packet with a sequence number that your browser or software is expecting. Once that happens, that person could redirect your traffic to a spoof web page, or they could even inject code using a crafted HTTP header in JavaScript. In this illustration, we can see what quantum insert would look like. Typically, quantum insert involves TCP hijacking after the TCP handshake when the target makes their first GET request. As stated in previous paragraphs, the hijack router tips off a shooter, and then the shooter beats the response back to the intended server, and at that point, we're able to hijack the TCP stream. After the TCP injection, a malicious actor would use a modified HTTP header response to either redirect the target to another server with a 304 redirect and serve a spoofed web page, or to run arbitrary code using JavaScript. In the illustration, we have a sample HTTP GET request header as shown in red. We can see a normal GET request for the host, JSONIP.com, using curl as the user agent. In blue, we can see a sample HTTP response header from the shooter. It is important to note that in the sample response that the shooter manually sets the value for the header content length. The reason the shooter has to set the content length of the header is that when the TCP packet are coming back to the target, there will be packets with duplicate sequence numbers coming in one after another. How each operating system handles the incoming duplicate TCP packets with the same sequence number is different. For Windows, it takes the packet that arrives first and overwrites the number of characters contained in the first packet in the second packet to create a single packet. If you look at the packet that is crafted, you can see that the header content in the dotted line is the first packet received, and the rest of the header content is the second packet received with the same sequence number as the first packet. This is called TCP segment overlapping. So, if a malicious actor didn't set the content length, then the browser would read the rest of the header and it would find that it is a malformed HTTP header and would dump the response. But if you set the content length to 0 or set it to a specified number of characters, you can have the browser ignore everything else in the original response. This allows the malicious actor to have the target's browser accept the spoof HTTP response. There are a couple ways to detect a quantum insert attack. One method of detection is to see if there are multiple TCP packets with the same sequence number. If there are multiple packets, you should check the contents of the encapsulated data to see if there are any differences in the data. As duplicate sequence numbers can occur due to retransmissions, the only way you can distinguish between a quantum insert attack or a retransmission is to compare the contents that is currently encapsulated for any differences between the two TCP packets. In essence, you would be checking for any sort of TCP segment overlapping. Another way to detect for quantum insert is to check the TTL on the two TCP packets with the same sequence numbers. It is hard for a malicious actor to know how many hops away the web server he is trying to spoof is, and makes it almost impossible to spoof the TTL. Checking for any discrepancies in TTL between the two packets with the same sequence number can reveal a possible attack. Now we're going to look at some Wireshark files that contain some captured packets that can further help illustrate how quantum insert works. So in this first example, we're going to open this Wireshark file. You can see the first three captured packets are the TCP handshake. And then if you look right below it, there's the first GET request. So if we were to follow that TCP stream, we're going to see in red, like in the slides, that the red is the original GET request from the actual target. And then if we look at the response from the shooter, it actually gives back a status code of 200 OK with content length 5. And then the 5 is for the 5 characters that it inserted into the header. And then just keep in mind that everything after the 5 characters will get discarded by the browser because of content length 5 is set. Okay, so that was the first example. In the second example, we can actually see a redirect. So we're going to open this Wireshark file, and same as before, same as the last example, the first 4 packets are the handshake itself, and then if we follow the stream of the first GET request, you can actually see the original host that the client or the target was trying to connect to is /dot.org. And then when you look at the actual response header from the shooter, it gives a 302 and then a 302 status code, and then a 302 is a temporary redirect. And if you look at the location is set to http ://fox-it.com. So that is not the original site that the target was trying to visit. Yeah, and then also you can note content length is set to 0 as well, so that way the browser ignores everything after. Yeah, everything after the content length. And I got one last example. It would be this example here. So this one's a little bit harder to find. So we actually have to use a filter to locate it. We're going to type in tcp.analysis out of order, and then we're going to filter out for an out of order TCP segment or packet. And then we're going to actually follow that stream. And then as before, you can actually see the original GET request in red again. And then the host it was trying to connect to was platform.twitter.com. But instead, if you look right here, back in the shooter response, it also gives its status code 200 OK. And then if you notice, it says content type text/JavaScript. So you could actually see that there is arbitrary code being injected into the browser to cause the browser to pop up a prompt, and then it redirects you to a web page. Yeah. So those are the examples that I got to show what quantum insert looks like on actual packets.